Okay, so we were looking at like where the asymptotes are, and then like what happens with like a number out front or like a number in front of the like theta or x, whatever. So I'm gonna look at a couple things about this. The number in front here, that tells us if it is like a shrink or like an expansion. And so whatever it is, it's 1 over that number is how we get that factor. So that's where that 1/2 came from. And then if it was negative, it, like we had said, we just flip it over. Now, vertical asymptotes occur at odd multiples of pi over 2, but if there is a shrink factor like this is actually going to change where our asymptotes are. So that's why I wanted to fix that. So our asymptotes are going to be at pi over 2 times whatever the shrink factor is. So in this case, 1/2. So this is going to end up being pi over 4. So our asymptotes on this one are actually going to get shifted to pi over 4 instead. Meaning I'm going to need to rein this graph in a little bit. Or actually, the easier thing would be just to change these to pi over 4, wouldn't it? Then I don't have to change anything else. Work smarter, not harder.
That pi over 4, that's the one with the asymptotes there.
Which one?
The blue one.
Well, yeah, the blue is the modified, the shrunk one. It's the one that has had the most, like the stretching, compressing stuff happening to it.
So why wouldn't you just leave the things at like pi over 2 and then use the things that are closer in? Because like you have like a whole like marking.
Because we don't change where our asymptotes are. Like our asymptotes would be in the same spot. Like, when I start out, I'm going to put the asymptotes on there where they're supposed to be. So I was just saying, like, the asymptote should have been at pi over 4 instead of pi over 2. So I just changed that so I didn't have to redraw the whole thing.
Also, yesterday I was wondering why the 4 tangent of theta and tangent of 2 theta, why those modified graphs look so similar.
Yeah, that's why I was confused about 2, because in the book, wherever I was getting them from, that's how they looked, and I thought that was weird. That's why I went back and looked at this to figure out what was going on with that. The period of this one would have been, so typically the period is pi, but because of this, again, it's going to end up being pi over 2 for this particular graph. So that means that one full cycle occurs in the range of pi over 2. Let's see, I read something about the numbers out front. Let me find it to make sure I say it correctly. Losing things too much. Where is it?
What?
That's
That was insane.
what I thought.
Losing books
Do you
over
want
here.
one?
Computer.
Okay, one for me.
So Jack died from having music on yesterday.
My supply comes from like a 64-ounce container.
I wish they made dark chocolate ones.
Me too.
I always look for them, but I don't know anything.
I love dark chocolate.
So it's apparently a dilation if the number is in front of tangent, and it's a shrink if it is before theta. It appears. So basically the difference is this one like goes more straight up, and then the other one is supposed to be a little more curved probably than it kind of looks on there.
So like the first one.
But the gist of it is there.
So the first one will still go out to like pi over 2, so it may like
Yeah.
go,
Because there's nothing in front of theta.
like it seems like it goes up and down faster, but it'll still get to like the same point. But the other one,
Pretty much, yeah.
it won't get as far from going.
Because it can't go out
asymptotes.
past pi over 4. So yeah.
I think I'm understanding this.
So let's just say we wanted to just talk about the transformations of this one. Or like what's happening. Well, we won't actually graph this one. But let's see. 3 tangent of 4x plus pi over 4 plus 1. Says, it just says to list the transformations that are occurring to this function.
Oh, so we don't have to grab it?
No. So this one, we've got a vertical dilation by the number that's in front, so by a factor of 3. This number out here we're going to look at for the period. So the period of a tangent function is pi over b. So the period is going to be pi over 4. What else is happening to this?
One.
Up 1. What else?
Left pi over 4.
Left pi over 4. So it kind of looks like they just have you graphing like the ones that just have like one thing happening, like these up here where there's like one thing, but then the rest of them they're like just explain what's happening. So we could graph this one. We would just be shifting it and stuff like that. And they don't like actually draw their asymptotes on their graphs, just like more of an FYI. I just mainly do it so that you have like a reference and can make sure you're keeping it in the right general area. Let's see. All right, so let's look at some just like key features of each of the other kind of trig functions, and then I will give you some tangent problems to practice, a couple to graph, and then some just to like explain what's happening basically. All right, so let's see, key features or key characteristics of, then we'll start out with secant. The period of a secant function is 2 pi, just like cosine. Wherever cosine of x is equal to plus or minus 1, secant of x is also equal to plus or minus 1. The graph of y equals secant of x has asymptotes at the values of x for which cosine of x is equal to 0, because that would be a 1 over 0 for secant, which is a problem. A local max for y equals cosine of x is the same as the local min of y equals secant of x and vice versa. So meaning like a local min of cosine is a local max of secant. And then the range of the secant function is negative infinity to negative 1 union 1 to infinity. And we do include the ones. And you'll already have all the parent function graphs, so we don't need to do that. Let's see, we'll do cosecant next. So a lot of these things are going to sound similar because cosecant and secant are obviously very similar, just in that they relate to, or cosecant relates to sine versus cosine. So cosecant, the period is 2 pi, just like sine is. Wherever sine of x equals plus or minus 1, cosecant of x is equal to, I just wrote the wrong thing, cosecant of x is equal to plus or minus 1. The graph of y equals cosecant of x has asymptotes at values of x for which sine of x equals 0. So for the same reason as secant at cosine equals 0. There is a local max for y equals sine of x, and it is the same as the local min of y equals cosecant of x, and again vice versa, the opposite is also true. It is a min for sine, it's a max for cosecant. And then the range is also from negative infinity to negative 1 union 1 to infinity. And then lastly, we have cotangent. So the period, just like tangent, is pi. the graph of y equals cotangent of x has asymptotes at values of x for which sine of x is equal to 0. Do you know why that is?
Because sine is the same as y, and cotangent is 1 over tangent. Tangent is sine over cosine, so then it would be cosine over sine.
Yep. So, yes, exactly. Cotangent is equal to cosine over sine, and so that's where that would cause a problem.
I totally could have said that in a lot fewer words.
You've been doing that a lot recently.
It's fine.
I was just along for the ride. I tried to keep up, but then he went like a tangent, and it was just too much.
Oh yeah, I went on a lot of tangents.
Yeah, just a few.
That's a good one.
The graph of cotangent is decreasing between consecutive vertical asymptotes. I'm just gonna write VAs. And then the last thing, the cotangent function has no amplitude, just like tangent. So the multiple choice questions for this stuff, even going back to sine, kind of look like it'll say the graph of which equation has an amplitude of like x, like it'll give you some number, and then a period of y. Okay, and it gives you some number, and then it gives you like 4 or 5 equations, and you have to pick which one meets that requirement. One of them, they give you, like, they could give you a graph of, say, like, the right side of the graph, and it'll say which equation makes sense for this graph, or, which equation is the function for this graph. It's not really you graphing it, so you shouldn't really have to worry about that. You just need to be able to, if I see a graph, I need to be able to explain what it is. Or it might be like they give you a function and then it says which of the following graphs is the graph of this function. So they might give you like 4. And so my recommendation is probably like graph one cycle of it on your own and then look and see which one matches is probably the easiest thing to do. Or like you can see what the amplitude is to start with of like a sine or a cosine graph. And be like, okay, well, if the amplitude is supposed to be 4, but this one, you know, I have 2 answer options where the amplitude is 2, I can get rid of those automatically. Just to kind of help you to visualize it. The other thing they do with, like, tangent, it looks like, is they'll say, here's your function, where's the vertical asymptotes going to be based on that. And so that would be kind of the things that I would say be more worried about, not so much the graph itself, but like being able to find those things about where those occur. So, any questions on that? More than likely on the quiz, or I may wait and do it on the test, we'll see. I'll have you graph all 6 parent functions just to make sure you know what they look like. But if you want to do, like, cosecant on the same one as sine, like, that's fine, so you don't have to, like, do it twice. But just, like, maybe do it in, like, a different color or just, like, draw a line, too. I mean, I'm going to know which one's which, but just so I make sure you know which one's which. So, any questions about that? Okay, so the book doesn't really have good questions for this, so I found 2 worksheets. I'm gonna look and see. I'm gonna go make a couple more copies of it so that y'all can each like actually have a copy. But we might just like highlight a few for you to do then when I do that. So.